Well, as you can see on your screen, I have, actually I'm just found this, I'm supposed to have a video in here in this week 8 under determining coefficient of curvature and coefficient of uniformity using the grain size distribution curve, and then it's got like, there's a video there. Well, I looked and it's not, so I'm going to put one there. And now we've been through some stuff like percent passing, and we've gone through some steps to lead us up to what we came here for, you know, to classify soils. So think about where we've been, and you can see we're in calculating grain size distribution. How big are the particles? How well spaced are they? That's the distribution part of it. The sizes will be reflected here in just a little bit when we determine the coefficient of curvature and the coefficient of uniformity using a distribution curve. So this video I'm going to put together, it's going to show us how to determine these coefficients, how to calculate them, and then those coefficients are going to tell us something about the soil depending on the number. Like I'm thinking like a higher number means a more spread out distribution, which is good, and versus you know, where you have one size all the way through your sample. That's not good. Think about a jar of marbles. If you put different size marbles throughout that jar as you're filling it up instead of a single same size, you're going to have a lot. If you put the same size, you're going to have a lot of air voids in there, so that's not going to be a very good soil. It's going to settle, etc., etc. So this tells us about those kinds of things. I'm going to go ahead and open this up. There, you'll see something that I'm going to explain, which is part of the video. I don't know why I said that. That sounds kind of silly, what I just said. But let's just read up here. The coefficient of uniformity, which is Cu, and the coefficient of curvature, which is Cc, are numerical values used in soil mechanics to describe the particle size distribution of a soil sample, essentially telling us how well graded the soil is, meaning how evenly distributed the different particle sizes are within the material. A higher Cu, once we calculate this, you'll get a number. A higher coefficient of uniformity indicates a wider range of particle sizes, way, you know, from big to little, you know, and all throughout different. While the coefficient of curvature reflects the shape of the particle size distribution curve, with values between 1 and 3, generally signifying a well-graded soil. Now this right here gives you a little view, a graphic of what we just talked about. As you can see, the sizes are down here and up here, like the 3/8, 3/4, the number 10 sieve, you know, etc., etc., etc. And the size of those sieves you can find down here. So we're looking at a similog graph, and it goes, in this case, it goes from right to left numerically. Look at this number here, that's 10, and this is 100. That's pretty small, so it goes 100, 200, 3, 4, 5, 6, 7, 8, 9, 10 hundredths, which is 1/10. So this right here is 0.1 millimeter. Now you can go 0.1, and the way you count it, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're at a full millimeter now. So there's 10 spaces between these things. As you can see, this is a graphic representation of using trigonometry and log 10. It's just that you don't need as many numbers. Okay, so that's how we read this. This is the particle sizes down here. Now this is percent passing. What size particles pass 10%? What are the particle sizes that pass, where 10% pass through a sieve size? Now take this line and go straight across until you hit the curve. Okay, there we are at 10%, and we go down to 1 millimeter. That's the size particle that passed that. Now, what size particles pass the 30%? We're 30% passing through a sieve. You go over here, you hit the curve, you go down, and you have, let me read that, 1,000th, 1/10, you have 100, you have a tenth. So that's a tenth of a millimeter right there. So these don't mean anything yet, except we're determining particle sizes. Now, to calculate the coefficients, which will tell us, as we described up here, whether we have a well-graded or a poorly graded soil, or the size of the distribution. So the diameter, this is D10. What is D30? What is D60? Well, this is, what is the diameter of the particles passing 10%, that are 10% passing? Well, 0.09 millimeter. If you go over here, you'll see 0.09 millimeter passing the number 10. The number 10. Over here, what the number 30%? What size were the particles that, what diameter were the particles that pass at 30% passing? So let's go over here and find 30%, go across, go down, and you'll see that it is 1, 2, 3, 4. A tenth would be a tenth. I'm sorry. Yes, that's a tenth. This is 1, 2 tenths, 3 tenths, 4 tenths, 5 tenths. I don't think that's right. Let me see. 10. Where is the 10? The 10, the 10. I had them. There is the D10. So the D10 is 9 millimeter. We did that a while ago. And the D30 is 19 millimeter. So that would be 0.2. So that's 0.1, 0.2. So there's the 30, and that's 19 millimeter. And the 60 is 41 hundredths, or 0.41 millimeters. Now, where is the 60? Well, it's over here, and it's down, and you can see 30, 1, 30, I'm sorry, there's 0.1, 2, 3, 4, 0.41. So there's your 0.41. Now, past the 60. So now the formula for this is, for uniformity, is the D60, the 60% diameter divided by the 10% diameter particle. And then we change that to these numerical values. 0.41 divided by 0.09 equals 4.56. So that is the value for the coefficient of uniformity, 4.56. Same thing over here. We substitute, but this is squared, so we have to take the D30 value, which is 0.19, and we got to square it up here, and then we take the D60, which is 0.41, multiply it times the D10, which is 0.09, and whatever that figure is, I forgot I could do it in my head, but you take that, multiply that, and take 0.19 and divide it by that answer, and you'll get 1. So that's a pretty small number in comparison to that. Now go back up here. Values between 1 and 3 generally signify well-graded soil. Okay, here's a value between 1, that's down to 1. Now, so let me read that whole thing up here. The coefficient of curvature reflects the shape of the particle size distribution curve. So values between 1 and 3 generally signify a well-graded soil, and values between 1 and 3 will usually get you somewhere with a curve just like that. Up here, the coefficient of let me skip that. How well graded is it, how even distributed it indicates the curvature. Coefficient of uniformity indicates a wider range of particle sizes, while the coefficient of curvature reflects the shape of the particle size distribution curve. So we have a well-graded soil here just by looking at this. But to get to this point, we had to go through these calculated by reading it from the SimLog from right to left. We were able to take the formula, which is, I have a fly on my screen. Here it is. Here's the formula for uniformity is the 60% diameter divided by the 10% diameter, which is 0.41 divided by 0.09. And the coefficient of curvature is the 30% diameter size squared divided by the 60% diameter times the 10% passing diameter, which is right here. So we have a 1 and a 4.56. So that's going to be a well-graded soil in both cases. So that's it for that, and I'm going to stop now. If you really want to get deeper into it, it's in your book. It's somewhere after you read about the Atterberg limits in your book. You might want to dive deeper a little bit in here. But just remember that this is the way you find it. You go to whatever percent you're talking about. You just take your ruler, go across till you hit the curve, and go straight down, and whatever it reads on that SimLog graph, or in this case a tenth, that would be the value right there. We called it a 0.09 because we weren't quite to this line. Okay, that's enough chatter for me. I'm going to stop this right now, and hope you enjoyed it.